Hello everyone. In this video, we're going to be looking at partial differential equations. And we're going to start with the very basic ones. That's why I call this video PDEs from scratch. I'll try to show you how you can solve basic partial differential equations. And then we're going to go into more and more complicated ones. And in this video, I'm also going to be introducing the method of characteristics. We'll talk about that for the last two problems. So let's go ahead and get started. But before we start solving PDEs, which is partial differential equations, let's do a little bit of notation. So when we say partial, for example, u is a function of x and y, a function of two variables. But here we're talking about the derivative of u with respect to x only. That is the partial derivative. And this is the type of notation that you use. But there's a shortcut. When you write u sub x, it just means the derivative of u with respect to x only, which means y will be considered a constant, okay? And then when you say u sub xx, it is the second derivative, and both derivatives are with respect to x. So you can also write it as the derivative of the derivative. That's why we get this type of notation. And when you look at u sub xy, that makes more sense, because what happens is, first we differentiate with respect to y. So that is the derivative of u with respect to y, and then we differentiate with respect to x, which gives us this type of notation. But again, instead of writing this gigantic, ugly expression, we do go with u sub xy. And by the way, what happens if you change the order? If you have a smooth function, which most functions are, right, the order is not gonna matter. So u sub xy and u sub yx are usually the same. Okay, so that's a little bit of notation, which is going to be helpful. So we're going to use these shortcuts. And let's go ahead and start with our first problem, which is going to be very basic. So we can start with something like u sub x equals y. So what are we talking about? We're talking about a function of x and y whose derivative with respect to x is y. So how is that possible? Let's think about the ordinary differential equation case. So suppose you have a function f and you differentiate it, right? And its derivative is equal to y. But in this case, y is a constant. Why? Because we are differentiating with respect to x. So let's just say f prime of x is equal to c. How do you solve this? By integration, right? Well, from here you can safely say that f of x is cx plus another constant. Let's just call that c1. Make sense? You could also call that c1, c2, whatever. But that's the whole idea. When you differentiate, you get constant. When you integrate, you get a constant times the variable, independent variable, which is x in this case. So same thing is going to happen here. Y is considered a constant. So from here, u is just going to be y times x, the constant times x, plus another constant. But you got to be careful when you solve partial differential equations. When you are solving or integrating with respect to x, remember, y is considered a constant, so the constant doesn't have to be a constant. It could also be something like a function of y. Does that make sense? So you can always check your results by the way, by differentiating this with respect to x. How do you differentiate this with respect to x? You've got to look at the coefficient of x. Think about it like 2x. How do you differentiate 2x? It's 2. So this will be y. And the derivative of f of y is 0 because it's a constant with respect to x. Does that make sense? So it checks, definitely. So the answer is y times x plus f of y. By the way, f of y is any function of y that's something that doesn't contain x in it. So it could be e to the power y, it could be cosine y, it could be anything you want, as long as it doesn't contain any x in it. Does that make sense? Great. Let's go ahead and take a look at the second problem. So for the second problem, we're going to do a little bit of a jump here. So u sub x is going to be yu. It's like why me, right? Okay, so this is a different scenario. Why? Because you do have a u on the right-hand side, which definitely changes the whole picture. We can definitely solve this problem with a different method, which I'm going to talk about later. But for right now, since we only have y and u, we can do the following. As you know, this can be written as partial u over partial x, and that's equal to yu. Let's go ahead and multiply both sides by 1 over u. So this is going to be 1 over u multiplied by partial u over partial x is equal to y. Now let's go ahead and integrate both sides, but you got to remember, we need to integrate with respect to x. So what is y is going to look like? It's basically going to look like a constant, right? Exactly. So here's what we're going to do. We're going to go ahead and first of all focus on the left-hand side. This is 1 over u. If you were integrating 1 over u with respect to u, you would say it's ln u, right? So let's just go ahead and write it. And I'm going to avoid absolute value here. I hope you don't mind. So this will give us ln u. But then what if u is a function of x and y, right? Then you would have to multiply this by the chain rule by the derivative of u with respect to x, which is exactly what you have here. So if you integrate this, you basically get ln u. Make sense? By the chain rule. And then the right-hand side, how do you integrate y with respect to x? It's just going to be yx. Think about it like 2x. 2 is the derivative of 2x. And y is the derivative of yx. Make sense? Great. Now, of course, we have to finish with a constant. And the constant, since we're integrating with respect to x, the constant needs to be a function of y. Remember the first problem? Our constants are functions in this case. And we can just go ahead and call that f of y again, since this is a different problem. Let's just call it f of y. Great. Did that give us the answer? No, not really. We kind of need to work this out. Let's do e to the power both sides. So that's going to give us e to the power ln u equals e to the power yx plus f of y. And then this will give us e to the ln u is just going to give us u is equal to e to the power yx times e to the power f of y. But here's what you need to remember. F of y is just an arbitrary function of y. So e to the power f of y is also going to be an arbitrary function of y, which is probably different in this case. And let's just call that g of y. You can use a of y, b of y, c of y, whatever. It doesn't really matter. But now you can write the solution as e to the power xy multiplied by g of y, which is again an arbitrary function of y. Now, if you go ahead and differentiate this with respect to x, and you're going to get y times u. That's what you should be getting. Of course, once you know what u is, yu would be more clear. I hope this makes sense. And I'm thinking about keeping this video short, kind of shortish, so that it's not too long and not boring. But now we're going to jump into the second order derivatives. So what about the derivative of u with respect to x, back to back, like the second derivative? So suppose this is equal to y. So what are we going to do in this case? This is not actually super hard compared to the previous one. Now, here's what you need to do. You kind of need to unfold this, okay? And to unfold this, you basically need to integrate, and notice that it's with respect to x both times. So if you integrate y with respect to x, remember this is a constant, so it's going to be yx plus you do need another constant at the end whose derivative is 0 with respect to x, so that needs to be a function of y, right? Great. This is the first integral. So, but I gotta write the proper thing. So if you integrate once, you get rid of one of these x's, so it's gonna give you yx plus f of y. If you differentiate this once with respect to x, you should get y. Now we're gonna integrate one more time because we need to unfold, right? One more time. So now u is gonna be, if you integrate, how do you integrate yx? It's kind of like a constant times x. How do you integrate x with respect to x? Isn't that x squared over 2? Yep. And just paste the constant. That's it, right? The constant rule. And of course, f of y is also a constant. So when you integrate it with respect to x, it's just going to be f of y times x, correct? And then we need to finish up with a constant whose derivative is 0 with respect to x. So that needs to be just another function of y. And there you go. You can kind of write it in a little way like x squared y over 2 plus x times f of y, which looks a little better, plus g of y. Now, f of y and g of y are arbitrary functions of y again. And if you integrate this, if you differentiate this twice, you should be getting y from here. You can always check that. But let me tell you, f of y can be anything. So I can replace f of y with y plus 1, y plus 1 cosine y. And this could be tangent y, e to the y squared, whatever, anything like that, okay? You have that much freedom. Since these are not initial value problems, we cannot really determine these constants, okay? Unless we're given those values. Great, let's go ahead and continue with number 4 and then number 5. Those two problems are actually going to be taking us into the world of characteristic curves, which is a fun stuff. So let me go ahead and give you, before I get into number 4, let's go ahead and talk about characteristics, how the chain rule works. So here's how the chain rule works for these kinds of questions. So you're basically going to have something like a times u sub x plus b times u sub y is equal to c. But a, b, c are not constants here, okay? They are functions. Functions of x, y, and u. Just think of them in terms of functions. I don't want to write a of x, y, u because that will look very confusing. I find it confusing at least. But here's how the chain rule works with derivatives. Now we're going to use a parameter here. And in this case, I'm going to be using s. S is basically a parameter that tells you where you are along a characteristic curve, which we're going to find out in a little bit. But here's how the chain rule works in this case. I'm going to replace a with dx over ds. Ux, as you know, is going to be like this. And then b will be replaced with dy over dx. Notice that how they're paired up. Multiply by the derivative with respect to y. And this gives us by this. Now think about it this way. Okay, x is kind of cancel out. That gives us the derivative of u with respect to s. But those are partial derivatives. And y kind of cancels out partial derivatives. That gives you the whole derivative, if that's the right word, I can't remember. But that gives you the derivative of u with respect to s, because we are talking about u as a function of s. So it's a single variable, and it's just going to be a normal derivative. Does that make sense? That is basically the chain rule. And let's go ahead and get rid of these lines. Oops, that gets rid of everything basically. But this gives us the following. At the end, you get du over ds. So if you're able to get that, c being the derivative of u with respect to s, that's going to give you an idea how u behaves. Okay, great. So these are going to be the coefficients, okay, in our equation. In this case, let's go ahead and apply this to a scenario. And I think that would be number 4. Great. Let's take a look at number 4. You have u sub x equals u sub y. So you're thinking about a function u of two variables. And when you differentiate them with respect to x and y, you always get the same result. How is that possible? Think about it. Now, first of all, I'm going to put these on the same side because notice that I do need this and I do need that. Okay? From here. Right? So let's go ahead and do that. Let's bring these onto the same side. Now let's go ahead and find out the coefficients of u sub x and u sub y. So we're going to write it like 1 times u sub x plus negative 1 times u sub y is equal to 0. So basically from here, this is going to be dx over ds. So dx over ds is going to be 1. dy over ds, which is the coefficient of y in this case, is going to be negative 1. And du over ds is just going to be 0. So basically, this method turns the PDE to a bunch of ODEs, which we need to solve. Let's go ahead and solve this. Now, how do we solve this? One thing you can do is try to associate, and it usually depends on the scenario. But in this case, notice that these two are opposites. This means that dy is equal to negative dx, correct? And if you go ahead and integrate both sides, from here you get the following. Y is equal to negative x plus a constant, let's just call that c. In other words, characteristic curves, which is these, are straight lines with slope negative 1. And what happens in this case, along these characteristics, along each line, y plus x will be a constant. But of course, for different values of c, we have different lines. Now let's go ahead and find out what happens to u. Remember, du over ds is equal to 0. So from here, you basically get a constant because the derivative of a constant is 0. Let's call that c sub 1. But here's the thing. The c sub 1 needs to be a constant, but kind of like a function of a constant, if that makes sense. So we're going to write it as f of c, which gives us the characteristic curve. So now, this basically gives us the following. U is equal to f of c, which is y plus x. You can also write it as f of x plus y. So basically, different characteristic lines can have different values of u, so that constant can be an arbitrary function of c. Does that make sense? I hope it does. Okay, so that's our solution. And again, if you integrate this, any function of y plus x is going to work. E to the power x plus y, tangent x plus y, 1 over x plus y, or just x plus y is going to work. Great, let's go ahead and continue with number 5, which is going to be the last problem in this series. Okay, number 5 is u sub x plus u sub y is equal to x. Now we're adding these two and we're getting x. And by the method of characteristics, notice that the coefficients are 1 and 1 here. So this is going to be dx over ds, which is 1. dy over ds is again 1. But du over ds, this is not homogeneous, by the way. du over ds will be x. Interesting scenario because this time du over ds actually kind of depends on x. Okay, let's go ahead and do this. What happens if I divide du over ds by dx over ds? And the reason why I'm doing that is because du over ds contains x and dx over ds is a constant, so we can divide and get a function of x from here, which is going to be helpful as you're going to see. So this gives us from chain rule, the ds kind of cancels out, du over dx, which is really cool because remember, use a function of x and y. If you can find something from here, that'll be super helpful. And of course, du over ds is x, so this is going to be x divided by 1, which is x. Awesome. Now cross multiply, you get du equals x dx. Now let's go ahead and integrate both sides. That's going to give us u equals x squared divided by 2 plus c sub 1. One thing to remember is this is an ordinary differential equation, so constants are not going to be functions because we're using a different method. And obviously, c sub 1 can be different for every characteristic. But where do the characteristic curves equations come from, right? Let's go ahead and now set these two equal because they are equal, and that's going to give us a relationship between y and x, which is helpful. That's what we need to find. So dy over dx is equal to, dy over ds is equal to dx over ds. And from here, you can safely say that dy is the same thing as dx. If you integrate, you're going to get y equals x plus a constant. Great. So from here, y minus x will be a constant. So basically, this labels each characteristic, okay? Now remember, u was written as x squared over 2 plus a constant c1, but remember what we said, c1 can be different for every characteristic that comes from here. Therefore, we're going to make it a function of c. So we're going to go ahead and replace c sub 1 with f of c, and this will give us u equals x squared divided by 2 plus f of y minus x, which is our characteristic curve. And this brings us to the end of this video. So let's go ahead and summarize the last two problems. The first example, in other words, the number 4, shows us characteristics carrying constant values. If you remember, du over ds was 0. And this number 5 shows that you can evolve as you travel along those characteristic curves. And this really brings us to the end of this video. Thank you for watching. Hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out SyberMath and aplusbi. And until next time, bye-bye.